Welcome to VerifAI's podcast series called Intelligent Verification. My name is Sandeep Srinivasan, and I'm the founder of VerifAI. This is the first episode in our podcast series. In this podcast, we want to talk about the challenges of hardware and software verification and how verification impacts security, innovation, and time to market. Now, verification impacts every consumer and developer on the planet. No consumer wants bugs in their hardware and software, and no developer wants to ship buggy hardware and software. Verification takes up more than 60% of the product cycle, and this trend is increasing due to the increase in complexity and the sheer amount of hardware and software that's being created today. At VerifAI, our mission is to speed up hardware and software verification by greater than 50%. In order for us to execute on our vision, not only do we need exceptional talent, we also need to learn from domain experts and their experiences. Therefore, I'm really excited about our podcast, where we're going to talk to domain experts in hardware verification, software verification, machine learning, programming languages, and many more topics. We at VerifAI believe that disruptive innovation comes when various domains intersect and there's a sharing of knowledge. I'm excited to introduce our first guest in our podcast series, Harry Foster. Hi, Harry.
Hello.
Harry is a luminary figure in the field of hardware verification. And Harry is currently the chief scientist for the Design Verification Technology Division at Siemens EDA, and is also the co-founder and executive editor for Verification Academy. Harry served as the 2021 Design Automation Conference General Chair, and he's currently advising Design Automation Conference 2022 and 2023. Harry holds multiple patents in verification and has co-authored 6 books on verification. Harry was a recipient of the Accelera Technical Excellence Award for his contributions to developing industry standards. In addition, Harry is the 2022 recipient of ACM SIGDA Distinguished Service Award and the IEEE Council on EDA Outstanding Service Award. Wow, Harry, that is quite a bio.
A mouthful.
Anything you'd like to add? Anything that I might have missed?
No, perhaps we could have cut it down, but I think it's great.
That's great, Harry. I'm happy that you're here. So Harry, please tell us about your journey. How did you start your career, and how did you get into EDA, and more specifically, design verification?
Yeah, so I started my career at Texas Instruments many years ago. At that point in time, I was actually doing IC design, ASIC design, and board level design. And actually, during that period of time, EDA wasn't like what we think about it today. Many big companies, TI, IBM, and so on, had their own, developed their own tools and stuff. So I moved from actually doing design to doing tool development. And I was all over the spectrum. It wasn't limited to verification. From TI, I left and went to work for Condex Computer Corporation, which was a supercomputer company based on air-cooled, basically air-cooled Cray class machines. You can think of it that way. And I really focused on tool development at that point. I did like ATPG, pattern generators, fault simulators, timing and power analysis, formal equivalence checking, which was one of my main research areas, and then got into assertion-based tools. But I left, Condex was acquired by HP, and then I left that and went to work for Verplex, which was a company back in the 2000 timeframe. Their main tools were equivalence checking and assertions. Left Verplex, went to Jasper Design Automation, and then I joined Mentor. And I joined Mentor about 16 years ago, and it's been quite a journey.
Wow. Well, thank you for that. What a fantastic career, Harry. And one of the things is both of us, one of the people we both of us know is Professor Jacob Abraham from UT Austin. Uh, and I think, Jacob has had a significant impact, just like yourself, on design verification, test, and the entire gamut. Jacob is also sort of theoretical as well as very practical. And the last time I spoke to him, he talked about his class at UT. And every time he talks about his class, he just sort of shows this great excitement. Now, I believe you teach verification or some courses in his class at UT Austin. Can you tell us a little bit more about this class and what your teaching philosophy is?
Yeah, it's a unique class in the sense that uh, he's brought together a group of industry experts as well as well-respected researchers for a series of lectures. So it's not just Jacob giving a lecture every week. It's all these invited lectures, and I've been involved with it, I think, since 2006, so quite some time. Uh, and each expert has their own area that they love to discuss. My passion is assertion-based verification. So I give two lectures, one on assertion-based verification techniques. We then go into system Verilog, the actual constructs and semantics of the language. And then a new course I've actually started picking up recently was SSC verification and validation, which is interesting because there it involves both hardware and software type of interactions. But my philosophy, I think, is in line with Jacob in that, for example, on the assertion-based verification, the first thing I do is introduce temporal logic, which is the mathematics, the foundation behind assertion-based techniques, and then I map system Verilog assertions onto that theory. Now, somebody actually might leave the course and never remember the theory, but
Yeah.
they will get out of the course and learn how to write assertions because we take practical examples with arbiters and bus interfaces and these type things and teach them how to actually write assertions. So I think really to answer your question, I'm a big believer in both theory and practice, and
Yeah.
practice is certainly very important for our industry.
That's excellent. Thank you. So it's fair to say when somebody takes this class, he or she is sort of ready for industry.
Yes.
Yeah, that's fantastic. So a follow-on question to that, Harry, is there was a recent study by Intel which shows that the enrollment for electrical engineering and computer engineering is significantly down as compared to, you know, 10, 15 years ago. Now, the most coveted major currently for young high schoolers to get into is computer science. Right? And even, institutions like large public institutions like UT Austin are offering more and more computer science, machine learning, data science courses in ECE, right?
Yes.
Now, I want to get your thoughts on this, which is why do you think the enrollment for ECE is down so much? Is it probably due to the hardware community not doing enough to encourage high school students? Is ECE too hard? I'd love your thoughts on this.
Well, I know, for example, at DAC, we put in place programs to encourage high school students to actually learn about our industry and get involved. I do think that's a pretty important, to help us solve this particular problem. But there's also another interesting thing going on. You mentioned, for example, that many ECE courses are starting to bring in data sciences as well as computer science and stuff. It's an interesting time in that, you know what a Renaissance man is, right? Renaissance man or woman, right?
Yeah,
Uh, these were people that were basically experts in everything. They weren't one-dimensional. They were multi-dimensional. And if you think about the complexity of our designs today, it's no longer one dimensional. You've got to have computer science skills. You have to have these data science skills. So it's interesting in that we do need to encourage more and more students, but we need to actually make them realize it's exciting. It's not just one dimensional. There will be many things you'll be exposed to.
yeah. No, that's great. That's a very, very interesting perspective. Uh, Now, talking about, you know, hardware verification and then let's say software verification, very few computer science students go to college to be a great software tester, right? But then hardware test and verification is sort of a different ballgame. I'd love your thoughts on this as to, what you see. Is it a specialization? Is it a subspecialization? How do you view this?
Well, maybe first comment, maybe there should be more students that go to for software tests. Maybe,
I completely agree.
I mean, the stakes are high, and we're going to get into some of the statistics later that we're seeing in terms of industry trends. But the stakes are high in terms of hardware. It is so critical. But one of the interesting things to me about uh, verification engineer, for example, I started, as I said, doing actually IC design, and I moved into verification and tool development. When I was doing hardware design, I could work on a project for 18 months or 3 years, long projects. I could do something of equal complexity in 6 months when it involved software and let's face it, verification engineer, a big part of that is basically a software project, right?
Yes.
So you have to have multiple skills there. You have to have domain knowledge of the hardware you're dealing with. You have to have unique skills associated with object-oriented programming, how to build coverage models, temporal logic, all these things in verification. I think it's exciting and it used to be that people treated verification engineers as second class citizens.
Yeah.
That is no longer the case. You go to any newspaper looking at the want ads, you're going to find significantly more higher demand for verification engineers. So that's where it's at. That's the reason these courses, like Jacob's course, as well as many other universities, have dedicated verification courses.
Yeah. That's a great answer. Thank you for sharing that. The other topic I think, which is very, I guess, close to your heart, is let's say formal verification, right? So, it's been over a decade or more, and formal verification is still used, very sparingly in the design community. So, is there anything missing? What is your perspective on this? Is has the innovation slowed down for some reason?
No, actually, the innovation it hasn't slowed down, and in some respects, it's even accelerated. Um, I will answer your question what the issue is and how to actually be effective at doing this. But
Yeah,
I also want to address the aspect about where are we in terms of adopting this, and I'm ignoring equivalence checking. I'm going to focus on formal property checking in these automatic formal apps. And so if you went back to 2014, you found that 26% of the industry had adopted formal property checking.
okay.
Today, that's 36%. Okay, that's only a 4.2% increase, CAGR. So it's incremental, but it is continue to grow. Yet, if you look at this, and that's aggregated across all design sizes, all market segments. If you look at this in terms of design sizes, designs over 10 million gates, you have 50% adoption. So significantly higher on
Right.
these larger designs. You also look at certain market segments like processors, significantly higher adoption there. Again, we see this slow growth. The question is, what is the issue? Well, I always like to describe it like this. If I came to you and you're a manager of a project and I said, I have this amazing tool that could do constrained random coverage driven verification. And here, just buy it. If you would to buy it, would you succeed? The answer is no.
Yeah.
Not until your organization matured and learned object oriented programming, how to create coverage models, and so on. So there's the maturing, the same thing in formal. You can't just buy a tool, write some assertions, and go. When
Yeah.
you get to really complex ones, you're dealing with, like, for example, properties are end to end in nature. That takes a tremendous amount of skill. How to address state explosion? What type of abstractions do I need to put in the design? Or way I write the assertions to actually introduce the abstractions there or the constraints. So that is skills that can be learned, but they must be learned. And without that, people buy a tool, try it out, and put it on the shelf.
Yeah. Yeah. So would it be fair to say that you have a lot of hope for the growth? I mean, we went to 36% of usage, and perhaps over the next decade, there'll be a significant rise in use of formal techniques. Yeah.
And I think a lot of where this growth is actually going to occur, and we're starting to see this, or these what we refer to as automatic formal apps.
Yeah.
Here, the user doesn't have to be a formal expert. They don't even have to write the assertions. The tool essentially can identify aspects of the design and create the assertions automatically. For example, it could go through and identify state machines and automatically check for live lock.
Right.
Uh, so they're very narrowly focused. They're not as broad as what I can accomplish formal property checking, but I do think we'll see a significant amount of growth here because they're much easier to adopt.
Yeah. Well, that's great, Harry. Thank you. Now, you've been conducting these research studies, Harry, on verification for a number of years. Can you tell us a bit about a background of these studies and what is the motivation and what are you trying to educate the public about?
Well, yeah, in fact, the studies date back 20 years. They go back to Ron Collette International, which conducted two famous studies back in 2002 and 2004.
Mhm.
They were the first and only industry-focused studies on functional verification, and they were limited to only ASIC. They didn't look at FPGA, and they were only limited to North America. Uh, Unfortunately, after 2004, Colette stopped doing these studies. So a mentor commissioned a new study based on the original Colette study, based on the original questions, so we could show trend analysis. And since 2010, we've been doing these every 2 years through Wilson Research Group. Now, the motivation is obviously to provide insight into where we are in terms of maturity in the industry. Where are the challenges at? So we gather a lot of data like this. It turns out that these studies are well respected and often, quite often, referenced in many research papers that are peer reviewed. We do a lot in the study to ensure that they're not biased.
Yeah.
And for example, we do not only survey our Siemens customers. This is in a way, kind of a double-blind study,
Yeah.
in that we know it's across all EDA vendors and so on. So, but anyway, it's been going well, and each year we learn something new.
That's great. So what is the makeup of this year's study in terms of topic, geographical participation, types of designs that you studied, market segments? Yeah.
Yeah, so we had this year 980 qualified participants. To
Mhm.
put that in perspective, that's like 4 times larger than the original Colette study in 2004.
Okay.
Uh, and it's, again, all over the world. We saw in terms of participation, 26% were from North America, 27% from Europe, 10% from India, 34% from Asia, and 3% from other regions of the world. We did have a decline in India, which is, in my view, somewhat a concern because let's
Ah,
face it, India's got some of the most mature verification teams in the world.
yeah.
And I monitor this very closely because that can introduce some lumpiness, slight deviations from year to year when you have one region increases and another doesn't. Um, but nonetheless, it's still, I feel good about the results, even with that slight decline in India. In terms of the targeted implementation, we found that 48% of the participants were working on FPGA projects and 52% on ASICs. And then market segments, it's all over. It's processor, wireless, cellular, networking, consumer, automotive, aerospace and defense, industrial, medical. We do track all these. By the way, one interesting thing we can do is actually filter down to a specific market segment and
Mhm.
look at that and compare it against overall trends. And that's something we often do.
Ah, wonderful. So two follow-on questions on this. One is, what is the margin of error and how do you sort of minimize any of these biases? I know you talked about double blind study. Uh, so a little more clarity on that would be great.
Sure, sure. So if you use a 95% confidence interval, this year's margin of error is plus or minus 3.7%.
Ah,
Now, What that means is a lot of people don't understand what does that really mean. What it means is if I would repeat this study 100 times, what I would expect to find is 95 of those times similar results plus or minus the margin of error. However, 5 of those times it might be totally out in the weeds. It is just some sort of anomaly in the study. We have seen that in certain times in the past on certain data points we suspect fell out of the confidence interval. There was one case in the last study where we saw this really huge uptick in terms of analog bugs. I suspected it fell out of the confidence interval. It
Yeah,
turns out it repeated this time, so it's not.
yeah,
It's
yeah,
so anyway. So these are things we try in terms of trying to minimize biases.
yeah.
One of the first things, this is an invitation survey that's done. A unique code is sent out, and then that code can only be used once. You
Oh,
can't share it with your buddies. You can't take it 10 times with your own personal biases.
yeah,
So we try to control that aspect. We also, as I say, I monitor regions of the world, and sometimes I will hit them with another request, to participate. We had an issue a couple of years ago in Japan that we discovered was because of the language issue. We were forced to translate into Japanese, and we continue to do that. And then
yeah.
we got our numbers up in Japan where they should be. So we do pay close attention to these and are looking for these type of biases.
Okay, that's great. So, what is the biggest surprise you found in this year's study? And what you mentioned India trending down. So perhaps you can speak to that a little bit, and then share what your biggest surprise was.
Yeah, so India trending down. My gut feeling is just an anomaly in this study because we've always had pretty good participation. Next year, next time we do it, which would be 2 years, we might make some other decisions. Maybe augment our lists that come from India, or try other things to figure out how to get those numbers back. I'm not really concerned about that, and even looking at the data, I do see some lumpiness that I know is due to essentially a slight decline in India. In terms of the biggest surprise this year was associated with the number of spins,
Ah,
and for years we've seen going back 20 years. It's
you mean
basically
silicon? You mean
yeah. If we
silicon
if
spins? Yeah.
yeah, if you went back 20 years and looked at all the studies, it had hovered around 30% of all projects were able to achieve first silicon success. The rest required multiples, and that had been kind of constant over the years. The uh, the surprise this year was that we saw only 24%, and,
Oh,
and
wow.
and we have for the past since about 2014 slowly have been seeing this decline in terms of achieving success. Now, the other aspect of that that's important to note is that we're seeing an increased cost in terms of wafer and mask. So even if we stayed at the 30%,
Yeah.
it's starting to hurt us because those costs are starting to increase significantly, particularly when you went from 24 nanometer down to 3 nanometers. Yeah. But the fact that we've got two things, we have the increased costs, but we have this downward success in terms of first silicon success. That is a surprise, and that's a concern.
Wow. So, is there any data that you've collected that would attribute first silicon success or failures to functional bugs or physical design bugs or physical design verification?
Yeah, in fact, we do actually track the root cause of various bugs, and there's many things that we're actually tracking from logical functional to clocking to analog mixed signal, power, timing, and so on. We track all this. The bulk of the issues, which is about 52%, are associated with clocking. Excuse me, with functional and logical flaws.
Hmm,
So anything a project can do to optimize that would be a big win for the project.
okay, that's great. Thank you, Harry. Anything new that you started to track this year uh, in your research studies?
Yeah, one thing new that we started tracking, it's something I've been meaning to track for the past couple of years, And that's related to the adoption of high-level synthesis and use of high-level languages. We find that 40% of FPGA projects have adopted high-level synthesis, while 30% of ASICs. That shouldn't be too big of a surprise, because typically you find FPGA projects, they're doing a lot of signal processing,
Yeah,
which today's high-level synthesis lends itself quite well to that.
yeah,
But from a long-term perspective, why this is important to me is that I feel the way we're ultimately going to get out of the verification crisis will be moving to higher levels of abstraction. That's how we've always dealt with complexity.
yeah,
And to put this in perspective, one thing that has been kind of a constant forever in our industry is the number of bugs per line of code. Whether it doesn't matter what language you're using, it doesn't matter if you're doing software, hardware, RTL,
right,
it doesn't matter. It's generally 15 to 50 bugs per 1,000 lines of code. It's been forever known. And that, by the way, that variance between 50 to 50 is due often to the complexity concurrency that's involved in the design. So why is that important? Well, if I can describe the design in 100 lines of high-level language versus 1,000 lines of RTL, I reduce my bugs by a factor of 5. I'm still going to have that same constant between 50 to 50, but there's less lines of code. And so I do feel that is something that's going to be pretty critical going forward as we continue to improve high-level synthesis to address the verification challenge.
yeah. No, thank you. So as a skeptic, I mean, I would say uh, HLS is like quantum computing, which is 20 years away from us, right? And 20 years ago, it was still 20 years away from us. So
But
is that
but
a
the,
fair assessment of HLS?
well,
Or
but the data does suggest it is being adopted. Like I
it is
said,
being adopted?
40% FPGA, 30% ASIC. But to your point, I cannot synthesize from a high level every aspect of design.
Yeah,
There's only portions of the design that I actually can apply this on. Uh, the holy grail would be someday I could do the whole entire design.
yeah, yeah,
Nonetheless, those that have adopted it or seen that benefit I talked about, the 10x reduction in bugs.
no, absolutely. I think the level of abstraction really, really helps, and it's helped us in our industry tremendously. Uh, so, did you, Harry, track anything related to machine learning, AI use, and its use in verification? I mean, that's sort of what Verify is all about. But I'd like your perspective.
We did track a few. Well, we tracked in general AI and then some specific things related to verification. And again, this was the first year, so well, it actually first year where we tracked AI accelerators. Uh,
Exactly.
and I'll talk about verification in a minute, but we were curious the percentage of AI cores that we were seeing in
Yeah.
designs. And what we found in 2020 was that 27% of ASICs claimed that they had incorporated an AI core in the design.
Mm.
That grew to 32% in 2 years. So that's one thing that we've tracked. We just started tracking that. It's an interesting trend, and we want to continue tracking that. The other thing we tracked was did the project incorporate some sort of AI or data mining technique in the overall flow? I'm not talking about a tool,
Right.
optimizing tool, but across flow. And what we found was that 17% of FPGA projects claim they had, and 21% ASIC projects.
Yeah.
Now, I don't know exactly how they're using this, but that's something that we can refine the question going forward. But it is an interesting data point. And again, I can't show trends yet because this is the first year that we asked that question.
Yeah, no, that's great. So we're seeing the same thing with our customers. There's a high adoption rate for all our AI solutions for verification that are sort of vendor agnostic solution, if you will.
Yeah, yeah.
Uh, so Harry, moving on to open source efforts and things like that. Companies like Google have significant compute and human resources, and I'd even go as far to say that we probably have more compute and human resources as Siemens EDA, Synopsys, Cadence, right? And these guys are, focused on building AI chips and things like that, the TPU, and they have huge teams that they're hiring. If you just look at LinkedIn or Indeed, Google is hiring tons of verification engineers in the CPU group, and so on and so forth. Now, are you concerned that companies like Google may hurt the EDA business model by open sourcing some of these high-end technologies? Imagine they, open sourced a coverage tool. Imagine they open sourced a formal tool that's scalable. So, do you worry about that as a Siemens chief
Uh,
scientist?
Actually, no. In fact, I actually welcome
Yeah,
the
great.
work in open source. I actually don't worry about that in terms of what its impact will be on existing tools. And part of the reason is I've been on both sides.
Yeah,
I worked on industry and I developed when there weren't solutions back then. For example, equivalence checking is a great example. That up to even when EDA introduced it, I could still outperform any tool with my equivalence checker
yeah,
that came out. Now, the issue is that my tool was amazing. It was optimized for the project. It could do some amazing things, but even within HP at the time when I was there, I couldn't use it on a different project. You know,
yeah,
that kind of scalability aspect is one of the challenges with open source and even best in class tools in that sense. So I do welcome, but I actually don't really fear that it's going to have a significant impact. I think we need both. Is
yes.
what I'm saying.
No, I agree with you. I think it's a very positive impact, and I would hope that the EDA community, especially the large three companies, would become a little more open, if you will, to ideas, software coming from the left field, so to speak. You know?
Yeah, I mean, some of that has happened over the years, and I think more will happen. For example, as we start integrating more AI across tools, I call
Yeah,
that AI around versus inside.
yeah,
Um, we are going to need much more openness to actually get this thing to work, and so I do think a lot of this will be forced on
yes.
EDA comes.
Great answer. Thank you. So, Harry, just a sort of more like a philosophical question, but also perhaps a business question and a technical question. What are you optimistic about in the field of design verification? And then what are your concerns in this area? Are we doing enough? Not enough? Um,
So let me start with concerns.
okay.
Uh, do you know who Deming was?
Yeah.
Edward Deming, Dr. Deming.
Yes.
Um, so
Quality.
yeah, so he
Deming
wrote.
Award.
Yes, yes. So he wrote a book out of the crisis back in the mid
I've read that.
1980s,
Yeah.
and um, he one of his claims in that book is that um, you cannot test yourself into basically quality. You can't test quality into a product. It has to be designed in.
Yeah.
And I do believe that we will be forced to reevaluate the way we're doing design today to actually improve verification. The problem is that their design happens and then it's pushed out, it's checked in, and then we have this huge backlog of bugs that are occurring. Many of them could have been prevented if somebody had simply run Lit, or maybe they ran one of these formal apps. I hate that term shift left, but we do
Yeah.
need much more of that happening to get to the point where we're not verifying quality into a project that we're designing it into to begin with. So I do think that's going to be critical. What was the other part of your question, though? Because there were two parts.
Uh, yeah. So, what are you optimistic about in the field of design verification?
Well, I'm optimistic. And basically, what's happening with AI and ML, and the reason I'm optimistic by that, if you look at DAC in terms of research papers that have been submitted, by far the largest growth area, significant growth area. It's been almost like its own Moore's law doubling.
Yeah,
Um, it has to do with AI and machine learning being incorporated in tools and across tools. So that is exciting. It's something new, and it opens new opportunities.
fantastic. So finally, what is your advice for the next generation DV engineer?
Simple: be a Renaissance man or woman. Don't be one dimensional. Uh, you know, it's important to pick up skills like Python. It's important to learn about you know data analytics, AI, ML. Again, you look at it as an opportunity to learn all types of new things, which will be required for as designs get more and more complex. So it's a great time to be in our industry.
Yeah, thank you, Harry. It was a pleasure chatting with you. Thank you for sharing your insights. And I think there's some wonderful, deep insights that you've shared along with data to back it up. And I really love your enthusiasm and energy and your continued contribution to EDA and the design verification community.
Well, thank you, Sandy. This has been fun.
All right. Thanks, Harry. Bye.